My name is Yong Liu. I work for Outreach. This work is a collaboration between Outreach and Databricks. It's my great pleasure to co-present this together with Corey from Databricks. The title of our presentation is High-Performance Transfer Learning for Classifying Intent of Sales Engagement Emails, an Experimental Study. So this talk not only discusses outreach data science research, but also showcases our experience with MLflow, a Databricks component, and how it supports our experimental study. So here's the outline for today's talk. So we'll go over our data science research objectives, and then I will give a brief introduction on sales engagement platform, which Outreach product belongs to. And I'll talk about some motivating use cases and technical challenges associated with email classification in this kind of platform. We'll talk about the experiments we need to run, the data sets and the results. And then we'll talk about how we integrate MLflow and how MLflow helps us to track all the experiments. And finally, summary and future work. So here is our data science research objectives. The overarching goal for this project is to establish a high-performance transfer learning evaluation framework for email classification. We'll talk about what qualifies as a high-performance transfer learning in the later slides. There are 3 research questions we would like to answer through this study. First, which embeddings and pre-trained language models to use? Second, which transfer learning implementation strategies to use? There are commonly 2 implementation strategies, feature-based versus fine-tuning. Feature-based approach usually just takes the pre-trained embeddings, uses them as featureizer, and then build models on top of it without touching the original model parameters. Fine-tuning basically takes the original pre-trained models and then fine-tuning the original model parameters. But it's an open question which one to use is more effective. So we would like to find out. And then finally, how many labeled samples are needed for such transfer learning? And we would like to find out all these answers through our experiments. So before we get into the details of the research, I would like to briefly introduce sales engagement platform. So how many of you have heard of this concept, sales engagement platform? Okay, maybe just a few. So this is actually a new category of software. Right now, Outreach product is one of the leaders in this category. Without a sales engagement platform, sales reps usually need to deal with a lot of disparate systems such as Gmail, Outlooks, calendars, meetings, phone calls, and then also need to manually enter them into a CRM system such as Salesforce, Microsoft Dynamics, SAP. With a sales engagement platform such as Outreach, sales reps only need to deal with a single system of action, and that is a game changer for them. It dramatically improves their efficiency and effectiveness. So you may wonder what exactly a SEP can do. SEP actually encodes and automates sales activities into workflows and pipelines. So on the left of this slide is a screenshot of how you can configure a sequence of activities into a workflow on Outreach product. So it actually automates execution and capture of activities such as emails and records in a CRM system. It then also schedules and reminds the rep when it is the right time to do the manual tasks, such as phone calls or custom manual email. So the end result is it enables reps to perform one-on-one personalized outreach to up to 10 times more prospects than before. So this is really good. So you may wonder what and why an email intent classification is needed in such a system. It turns out email content is critical for driving results for prospecting and other stages of the sales process. A replier's email's intent-based metric, such as using positive, objection, or unsubscription to measure the reply rate, is much better than a simple reply rate, because not all replies are created equal. A/B testing using a better metric can pick winners of the email content or template much more confidently. So this is super important. However, email intent classification is very challenging on a SEP system. There are two primary reasons. First, a SEP system covers the entire sales process from prospecting all the way to closing. And it also has multiple orgs. When we say orgs, we mean different kind of customers. So for example, Outreach has over 3,000 customers across different industry segments and different size, such as Adobe, Databricks, or Zoom. They are all Outreach customers. So they have different contexts and different players along that sales process. So this could significantly change or add the context change into the classification process. Secondly, there are limited labeled sales engagement domain emails available. Currently, there's no open or public domain sales engagement email corpus. And due to GDPR and privacy and compliance constraints, it's unlikely there will be any public or open corpus for such purpose. It is also very time-consuming and even not possible to label emails in many orgs on an SEP system. So it's certainly not possible to label over 3,000 orgs emails at Outreach. So that's why we turned into transfer learning. So there were lots of talks actually today mentioned about transfer learning. So in a simplified way, transfer learning can be described training a model using a corpus or a domain data and then apply that model to another domain or a corpus. So in the case of pre-trained language models, they are usually trained using open or public data set such as Wikipedia books corpus. And then we could use that kind of pre-trained language models to apply into sales engagement domain emails. So potentially, it opens doors for high-performance transfer learning. So when we say high-performance transfer learning, we mean we could use fewer training examples to achieve better accuracy with reduced model training time and engineer complexity. Pre-trained language models such as BERT, which is released by Google, have achieved state-of-the-art scores in the NLP GLUE leaderboard. So this is very encouraging. However, whether such benchmark success can be readily translated to practical application is still unknown. So that's why we conduct this research. So we select 4 pre-trained language models and embeddings for our experiments. The first one is called GLOVE. This is a classic count-based, context-free word embeddings released in 2014. So word embedding is an n-dimensional vector of real numbers to represent word. A context-free word embedding means that as long as it is the same word, that representation, that vector is the same. However, in last year alone, there are quite a few so-called context-aware embeddings or pre-trained language models were released. So we select 3 of them for our experiments. Elmo is the first one, built on top of recurrent neural network architecture. It's a context-aware character-based embedding. Flare is another one, is a contextual stream embedding. And then finally, BERT. It is the state-of-the-art transformer-based deep bidirectional language model released in late 2018 by Google. So having select those pre-trained language model and embedding, we then prepare some of our in-house outreach-owned email dataset for this experiment. We annotate these emails into 4 categories: not sure, objection, positive, or unsubscribe. And as you can see, this is also a very imbalanced data set. Objection has the most number of emails. So this adds additional challenge for a machine learning model, as you see that imbalanced data set is difficult to classify. So to give you some ideas what those intent or emails look like, this slide shows some examples. For a positive intent, the email could read, actually, I'd be interested in talking Friday. Do you have some time around 10 a.m.? For an objection intent email, it could read, thanks for reaching out. This is not something I'm interested in at this time. And then for an unsubscribe intent email, it could read, please remove me from your email list. And finally, not sure is basically the replier is not sure about the context of the email, or they want to ask some clarified question, etc. So it's really hard to quantify the intent. So we put it as a not sure label there. So given that kind of data set, we designed 2 sets of experiments. The first set of experiments is to use different pre-trained language models and embeddings, and then compare feature-based versus fine-tuning-based approach using the 4 training examples. So the previous slide shows the 4 data sets, and then we split them into train and test and the development set. So for this first set of experiment, we then use the 4 training examples. The test set examples are always the same. For the second set of experiments, we use different labeled training size with feature-based and fine-tuning approach. We then want to study how that different approaches scale with different number of training examples. We use increasingly larger training size, ranging from 50, 100, 200, all the way to 3,000. So here is the results for the first set of experiments, which compares different embeddings using either feature-based or fine-tuning-based approach. For the fine-tuning-based approach, we only use the BERT as the fine-tuning model, as BERT is the latest state-of-the-art pre-trained language models. So as you can see, BERT fine-tuning has the best F1 score. So the y-axis is the micro-average F1 score, which is commonly used for multi-class classification problem performance metric. And then for all the other feature-based approaches, GLOVE actually is surprisingly performs slightly better than all the other combinations of the embeddings. We also compare with classic machine learning approaches such as light GBM using a TF-IDF as the featureizer. And it turns out it also underperforms BERT fine-tuning. So BERT fine-tuning is the winner when using all the training examples. For the second set of experiments, here's the result. So we studied the scaling effect with different training example sizes. So this chart shows different methods while the number of training example size goes up, right? So we only plot 3 curves here just for readability. So the blue line is the BERT fine-tuning approach, and then the other 2 is GLOVE, and then BERT with FLAIR. So as you can see, BERT fine-tuning outperforms all other feature-based approaches when training example size is greater than 300. So that's very interesting. 300 is a magic number for our use cases. It is the turning point for BERT fine-tuning to consistently outperform and continually ranked higher than other approaches. When training size is smaller, such as if the training size is smaller than 100, BERT with FLAIR combination actually performs better. In fact, with just 50 examples, BERT plus FLAIR achieves almost 0.67 F1 score. However, to achieve an F1 score greater than 0.8, which is usually the minimal bar we want, BERT fine-tuning needs at least 500 training examples, while feature-based approach needs at least 2,000 training examples. So in terms of high-performance transfer learning, we would say BERT fine-tuning is a high-performance transfer learning approach as it quickly rises to the top with very little training examples. And that's really exciting for us and promising for our problem domain. You may also notice that for each data point, there is an error bar there. So for each data point, plot here, we need to run at least 5 runs to measure the variance of the F1 score. So the error bar is 1 standard deviation of those 5 runs, and then the data points we plot here is the mean of those 5 runs. So as you can see, we have lots of runs to execute. And that's where MLflow comes into play to help us to manage and track all those experiments runs. So I'll give Corey the platform to continue the discussion.
Thank you, Yang. I'm going to spend the next few minutes talking about MLflow and explaining how MLflow has helped Outreach manage their model development processes. MLflow is an open source platform for the complete machine learning lifecycle. It was originally developed at Databricks and has several nice attributes. The first is that it's designed to work with any machine learning library and programming language, which means that Yang's team can continue to leverage the set of tools that are most powerful and that they're most comfortable with. Additionally, MLflow is designed for reproducibility, meaning that training code runs the same way anywhere, whether that's on a data scientist's local machine, on a cloud-hosted platform, or in a Databricks notebook. MLflow is designed for scalability, ensuring that it's just as useful for a large and well-established data science team, like the team at Outreach, as it is for a single data scientist working on their local machine. Finally, MLflow integrates tightly with Databricks, meaning that existing Databricks users can leverage all of the advanced model development and tracking functionality provided by MLflow. I'm going to provide a quick overview of MLflow's major components. The first is MLflow tracking, a centralized repository for all of the critical model training metadata within an organization. I'll also talk a little bit about MLflow projects, which is a packaging format for reproducible runs across platforms. This is what provides that consistency in training code regardless of the execution environment. Finally, the third component is MLflow Models, a generic model abstraction that ensures that any model produced by MLflow can be deployed to a variety of production contexts, whether that be batch, streaming, or real-time inference. I'm going to hone in a little more deeply on MLflow tracking, since this is the component that Outreach is currently using most heavily. There are two primary aspects to MLflow's tracking component. The first is a centralized service for aggregating all of the training sessions and their metadata within a data science organization. This tracking service is designed to be modular and to run on a variety of familiar production infrastructure, whether that be MySQL, Postgres, Amazon S3, Azure Blob Storage, or for simplicity, any Unix file system. The second aspect of MLflow tracking is a collection of lightweight APIs made available in a variety of languages that allow existing model development code and machine learning code to be instrumented in order to capture all of the important model training metadata. MLflow tracking can capture the parameters and metrics associated with a model training session, which provides valuable insight into model performance. It also provides APIs for capturing artifacts. These can be any arbitrary file, including serialized models, which means that as a data scientist, if I'm developing a TensorFlow model, I can save it, and months later, another data scientist or production engineer in my organization can come back and reload that TensorFlow model in the exact same state while retaining all of the important performance characteristics. Additionally, the tracking component enables users to record information about the code that was used to produce models. So as Yang's team develops and iterates on the code that is used to produce the model for BERT fine-tuning, all of the important source information and versioning info is maintained in the centralized tracking service. And finally, for any components that is not supported as a first-class concept in MLflow tracking, MLflow provides support for any tags and notes that data scientists training models may want to include. This could be a good place to include information about the business use case for a particular model, for example. So now that we're familiar with the tracking component structure and the collection of metadata that it is designed to support, let's take a brief look at some example code. In this case, we're looking at MLflow's tracking API in Python. It all starts with the initialization of a new machine learning training session via the MLflow start run directive. Once a training session has been initialized, users can log model hyperparameters using the log param directive. In this case, we show example code for logging the number of layers in a neural network, as well as the alpha parameter for a logistic regression training session. After this point, the user can simply paste in any of their existing training code. MLflow is not at all restrictive or prescriptive about the types of training code that can be used within a training session. Once a model has been produced, it is often evaluated against some test data to produce model performance metrics. These are collected via the log metric directive. Oftentimes, through the course of model evaluation and the obtaining of metrics, more sophisticated artifacts such as performance plots are produced. These can also be saved via the log artifact directive. And then finally, and perhaps most importantly for reproducibility, the model itself can be saved directly to the centralized tracking service. In this case, we demonstrate some example TensorFlow code using MLflow's TensorFlow integration that can be used to save a TensorFlow graph to the centralized service using a single API call. Now, once Outreach has developed a model that they're comfortable and confident in, their next step is to productionize it and start satisfying their business use case. For this purpose, Outreach is currently experimenting with the MLflow Models component, allowing the models produced in a variety of frameworks that they're using, such as TensorFlow and PyTorch, to be productionized quickly and efficiently across a variety of frameworks. For example, if Outreach wants to enable real-time analysis of emails as they're received, they can deploy their models using MLflow to platforms like Amazon SageMaker or Microsoft's Azure ML for real-time scoring. They may also choose to apply their models to collections of previously collected email data in order to perform more batch scoring and stream-oriented approaches. Now I'm going to hand it back over to Yang, who's going to provide a little more context and talk more in depth about how they've used MLflow to instrument and more effectively run and manage their model development processes.
All right, thank you, Corey. So we use MLflow to manage hundreds of experiments. We have primarily two kinds of models. First kind is PyTorch models, mostly for the feature-based approach. We use a framework called Flare, which is built on top of PyTorch. We also use TensorFlow for BERT fine-tuning. This is based on the BERT TensorHub framework released by Google. So hundreds of experiments are being recorded and tracked by MLflow. So once this is being tracked, we can go to this MLflow page and then query them using the search query by parameters, by metrics, and then we can also download them for post-processing, etc. And there's also another very useful features here is it allows us to track where the source code, which source code was used. So there's a source link here. This is the exact copy of the source code that was executed when this experiment was run. So regardless whether you change it later, this is the exact copy. So this is very, very useful for us to really track the changes and really examine what are the experiments changes we have made. As Corey mentioned, MLflow allows us to log artifacts, parameters, metrics, and models. So the API is very straightforward. So here is just an example I put here that how we use it. So in order to log the micro-average F1 score, we just use one line MLflow.log metric with the score name, the metric name, and then how we compute it. So if you record that we run like at least 5 runs, so we have 5 raw numbers of those metrics, and then we take a mean of that, and then that can be recorded here. And then you can also see like in here, there are lots of parameters we recorded here, and then the metrics here. There are also lots of artifacts can be recorded. So this is one of the examples showed here, which is the training history of the deep learning models. And we can also record the model itself is a serialized PyTorch model. So all these are being tracked and saved at MLflow check-in server. Images can also be logged as artifacts. And this is very important for us, not only just record the numeric numbers, but also the visualization results. So this slide shows the visualization results of BERT fine-tuning prediction results in a cluster kind of view. Each symbol on this cluster represents an email, and then the cluster represents similar intent of the emails. So they cluster together if they have similar intents. So as you can see, this is the unsubscribe group, which is nicely separated out. So that means BERT fine-tuning model can predict unsubscribe intent very well. You can also see the positive and objection clusters are also kind of separated out, but there are some kind of a mixture along the boundaries here. So potentially there are some kind of edge cases we still need to dig a little bit deep in order to make it work better. Not sure is the red dots here, which is kind of scattered, mixed with other two positive objection groups. So potentially that's also a very hard case to predict. But having this kind of visualized result is very important for us to iteratively further develop the model and also use this kind of mispredict examples to further refine the model. So the API to use is very simple. It's just MLflow.log artifact with the picture, and then the second parameter is the folder where you want to save this picture. So once you log it, it's saved. So along with all the other parameters, metrics, artifacts you see before. So this is tremendously useful for us to track all the hundreds of experiments we run. So in summary, we actually found fine-tuning BERT outperforms all feature-based approaches. So it is a high-performance transfer learning approach. And particularly in our experiment found, fine-tuning BERT works better when training example size is greater than 300. Pre-trained language models also solve the cold start problem when there is very little training data. So if you only have as little as like 50 labeled examples, and you want to just get started to see how it predicts, you may want to try BERT plus FLAIR using the feature-based approach, because it works actually better than BERT fine-tuning approach. So there's a trade-off there depending on how many training data you have. However, to get to F1 score greater than 0.8, it may still need 1,000 to 2,000 examples for a feature-based approach, or 500 examples for fine-tuning a pre-trained BERT language model, which is still doable. So finally, MLflow is proven to be very useful and powerful for tracking all experiments. And this is very useful, especially we have multiple people to run the experiments, modify the code, and then compare results. So next step, we are continually using MLflow to transition from experimentation to production. As Corey already mentioned, there are multiple ways to pick the best model for deployment. We will also extend our data science work to cross-org transfer learning, which means that we could use one or multiple orgs data with permission for training and then applying that model to other orgs. So this is super important if we want to actually release the feature in GA. So I would like to thank Outreach Data Science team and Databricks MLflow team for the collaboration, and we look forward to further collaboration on this area. Thank you very much. We have 5 minutes for some questions. Yes, there's a microphone there. Can you please go over there? Thank you.
Yeah. Which BERT model did you use, and how did you extract the vectors for the feature-based approach?
For the feature-based model?
Yeah, which BERT model did you use? Like
the uncased. The
small one?
Yeah, the small one.
Okay, and how did you extract the vectors for the feature-based approach?
We use the last 4 layers.
Okay.
Yeah.
Cool.
Yeah.
Thanks.
That's actually what they recommend.
Okay.
Yeah.
The graph that you showed, the TSNE dimensionality reduction graph, what was the input feature for that? Like, was that again the last 4 layers of the bird?
For the feature-based approach?
No. You just showed a graph with the groupings of different examples, right? The different training inputs. Like,
The artifact slide.
yeah, this one, yeah.
Oh,
So what was the input for this, for the TSNE thing?
oh, so this is the prediction results, the
Right.
test data set
Right.
that we use. Yeah,
Right.
so the input is basically the embedding after the training.
Okay.
Yeah, is the embedding.
Okay.
Yeah. So each email is represented by the vector.
Okay.
Yeah.
Did you see any changes between the embeddings before training and after training, or?
Oh, yeah.
Okay.
Yeah, I didn't show that because we don't have enough time to show that. Yeah, definitely, yeah.
Okay.
And also, like, for different feature-based approach, you can see the cluster shape is very different from, like, bird fine-tuning cluster.
Okay.
Yeah,
Thank you.
yeah, thank you. All right, if we don't have further questions, yeah.
Last one. So when I first started using MLflow, I probably spent like a whole day figuring out how to actually save a model to the file path, because I was using the DBFS :/, and I figured I got lucky. I stumbled upon using the fusion path. Is
Got
that
it.
just I didn't
Fuse
know what I
mount.
was doing, or is that the way you're supposed to do it? Use a fuse path?
That's a great question.
Because I saw like no documentation, because everywhere I was reading, it shows that they were showing they was saving their artifacts. But I was like, I'm trying to save it, but it's, you know, I didn't get the Spark message saying it doesn't know about the path or whatever. So
It's an excellent question. Just to clarify, you're saving a model that was originally written to DBFS, and you want to upload that as an MLflow artifact? So you,
I had a data set. So
Okay.
I had a data set that I saved off to a CSV file that was in the file store. And so I wanted to save that CSV data set as an artifact. And so when I put in the actual location of that data set, I used DBFS : and a data set, and it said that it couldn't locate the data set. And I kept just, you know, checking it. I was like, it exists. I know it exists. Why is it not working? And so I spent like a whole day just kind of trying out different things, and I found out about the fuse path of not using the DBFS : just the /DBFS /file store, and that worked. But
Right.
I didn't read any documentation of why per se, so I was
yeah,
curious.
it's a wonderful point, and I think it's a common point of confusion, and that's completely on us to improve the documentation. But the fuse mount is the recommended approach. Essentially, for logging artifacts, MLflow expects that the origin path be a local file system path. So that fuse mount allows the DBFS artifact to be interpreted as something that is local. In the future, we may support logging artifacts that exist in other locations. For example, you could log from an S3 bucket to MLflow, or you could log from Azure to MLflow. We're working on that kind of stuff.
Is that the same, even because I had the same problem last night, I was building a TensorFlow model, and I wanted to save the epoch of, you know, location so I could pick the best one.
Uh-huh.
But I ran into the same problem using the DBFS : and it didn't work until I used the actual fuse path. So I wonder if that's just built into most of the models you need to actually.
Right, yeah. Currently, it's either fuse mount or a local path. And yeah, we'll work on sort of expanding the support of origin path types. That's a super good question. Thank you.
Yeah, thank you.